Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Computational Gas Dynamics, week 2, normal shock wave and oblique shock wave. So, in our last lecture, I have completed the normal shock analysis. Then, in this lecture, that is lecture number 3, we will start the part 1 of oblique shock waves. So, in this section, we will deliberate our discussions with a Mach wave, which means it is the initiation of oblique shock wave formation. Then I will try to compare the normal shock analysis and oblique shock analysis, the actual viewpoint of when under what circumstances we call oblique shock and under what circumstances shock wave behaves as a normal shock. Like in our previous study, normal shock, which was considered as a one-dimensional flow analysis and for which we have derived the governing equations. With similar philosophy, we will also try to visit the governing equations for oblique shocks. Then we will frame the oblique shock relations to calculate the flow properties. So, in our normal shock discussion, what we have told that a normal shock wave is considered shock wave in which the flow when the flow crosses it, the direction of the streamline and the shock wave, they are perpendicular to each other, and it arises when the flow is supersonic and flow behind the normal shock is subsonic. And normal shock is analyzed with given conditions of upstream condition and the unknown values which we found from the normal shock analysis and normal shock gas dynamics table are given corresponding to the upstream Mach number, that is M1. So, these are the some fundamental relations which we have derived in our previous lectures. One is Frankel-Dehn relations that talks about relation between the Mach number after the shock and Mach number before the shock, and it is told that Mach number after the shock it is subsonic. Similarly, we have characteristics Mach number, we have static density and static and speed ratio before and after shock, static pressure ratio before and after shock, enthalpy and temperature ratio, then stagnation conditions means stagnation pressure ratio, temperature ratio and density ratio. Then we have derived another relations which is a Rayleigh-Peter tube equations. This is one of the case where we talk about experimental observation for normal shock, and this is a highly fundamental equations when you deal with wind tunnel experiments involving normal shock. We also showed that the static temperature remains constant, stagnation temperature remains constant across the normal shock. Then looking at the pressure and temperature ratio of static value, one can also find out normal shock entropy change across a normal shocks. This gives an indication that flow field across a normal shock is highly subsonic and irrotational. Now, we will start moving to or we will try to introduce a wave which is Mach wave. So, if you revisit our previous discussions, we started with the sound waves, then we talk about the shock wave. Now, we will talk about Mach wave. So, Mach wave is falls something between between a normal shock wave and a oblique shock wave. So, the philosophy of Mach wave comes into picture when you wave which is propagating everywhere in the flow field. To give the brief introduction about the Mach wave, we consider a point source starting at point A and it is emitting some pressure disturbances. So, obviously, these pressure disturbances will propagate everywhere in the flow field, and everywhere in the flow field with center at point A. So, we can have a infinite number of concentric circles that will talk about the distance travelled by the sound wave at a given time t. So, from point A, if you can draw a line delta t. So, if your sound wave velocity is a and with time t, so distance travelled by this sound wave will be a times t, and with a times t we can draw a circle and with center point A. So, what we see is that one particular instance of, let us say one particular instant we show this dark circle, and let us say that this distance is a times twice delta t. So, means at different time steps we can draw concentric circles, and distance will be the radius of that circle. And here this is at. So, here we assume that initial time t0 is equal to 0. Now, when this t0 has a finite value, then this number would be distance travelled by the sound wave will be a times t minus t0. Okay. So, this is this happens when the point source is stationary, that means a point A is stationary. Now, we can next assume that, let us say the point A starts moving and side by side it emits the sound waves. So, sound wave distance and when this point A moves at a velocity v, and at certain time t it will reach a point B. So, distance travelled by the point source from A while moving from A to B would be v times t, because this velocity of this is v, and correspondingly the sound wave will also have the radius with a times t at same time t. Now, since b is always less than 1 when the flow is subsonic, which means this Vt distance will be always less than a time t. So, this gives an indication that at any time whenever you draw this concentric circle, that is a times t, V time t will be always less than 1. That means, all these circles which was shown here, it will be always within that domain. So, physically it means that from the point A, when the sound wave moves, it moves at a faster rate. Now, when it moves at a faster rate, side by side it takes the information of information from the A and which spreads all over this circle, within that circle. So, when the side by side when the point A moves to B, so it also and this distance, this V times t distance is always less than a times t, which means at under any circumstances this the Vt cannot be greater than 1. In other words, it means that information about the presence of movement of point A to point B is being warned through the sound waves to the medium. So, this physical information is applicable only for the case of subsonic flow. So, we can spell out that by removing a point source, but for the timing if you just remove that point source A, and we can spell out in general that if a body moves at subsonic speed in a compressible fluid, the fluid ahead of the body becomes aware about the presence of the body, since the body emits disturbance signals in terms of sound waves ahead of itself. So, this is the summary what we have, what we see when the flow is subsonic. Now, let us say that point source is moving at a sonic speed with initial location A and subsequently reaching a point B at time t. So, when it is subsonic, when it is point source is moving at a velocity v which is equal to a, then this v t distance, that means distance a b is v t now and the sonic circle distance is a t now. So, both are equal. So, this boils down this physical information shown in subsonic flow to a sonic flow situation. So, we can draw a line, we can draw a plane x x at point B which is perpendicular to the, which is essentially tangent to the sonic circle. So, what we physical information we get here, that the zones that where sound wave moves, that means information is propagated. So, we call this as a zone of action. Now, beyond this point B and or a plane x x, the informations are not passed on because the passed. So, this area or this zone is not aware about the event. So, that is what it is called as zone of silence. So, what we can say that point B will lie on the pressure dispersion circle with point A at its center. A sonic circle is formed with a radius a b. So, what we can make summary that locus of leading surface of all the waves will be a plane passing through the point source perpendicular to path of the motion. Neither the sound wave can travel in front of the point source nor an observer in front of the source could hear the sound. That means, information is not propagated. That is what this zone is called as zone of silence. Wherever the information is propagated, that is called as zone of action, and this is separated by a plane x x passing through this point B. Now, let us see that what happens when the flow becomes supersonic. When the flow becomes supersonic, B is greater than A. That means, velocity of the body or velocity of that point source moves faster than the speed of sound. That means, this circles, that means point B starts moving towards this zone of silence. So, when it moves to this zone of silence at one particular instance of t, the distance travelled by this point source would be b times t, that is distance between A and B, that is b times t, whereas the sonic circle distance would be A times t. So, that means point B starts moving towards the left and there will be infinite number of sonic circles that keeps on forming with this the apex point being at B. So, this event is a very critical event. So, what we can say is that the when you for each sonic circle, if you can draw this tangent point and if you can draw a line starting from point B which is essentially tangent to all the infinite number of all the sonic circles which is formed during the time interval t, and for which the distance travelled by the body is v times t, whereas sonic circle distance is a t. So, if you look at this geometric nature of this figure, this and draw a line which is a tangent, draw a line which is radius of this sonic circle, and from this point C, if you can draw line B, so you have a BC line. So, this ABC is a rectangular triangle with an angle ACB as 90 degree. So, this angle is 90 degree. So, from this geometric information, what we can say that pressure disturbance envelope is formed through straight lines that are tangent to the family of all circular sound waves. Now, if you can extend this particular picture, so typically this appears as a wedge, and if you extend this wedge in a plane which is perpendicular to this plane, to the plane where or on this surface, then it will form a cone. So, in a 3-dimensional cone, the locus of leading surfaces of the wave is a cone with a body at its apex, and this cone is known as Mach cone. The line of disturbance is known as a Mach wave. So, through this Mach cone, we can draw this disturbance line of disturbance as a Mach wave, and half angle of this Mach cone is known as Mach angle, which is mu m. So, mu m is your Mach angle, and this entire things is called as Mach cone in a 3-dimensional plane. So, how do you locate the zone of silence and zone of actions? So, wherever we see the presence of sound wave, we call them as a zone of action, because informations are known or propagated, and wherever we find the absence of sound wave, we call this as a zone of silence. So, in summary, what we can say, the 3 different events, that is subsonic flow, where informations are always shared to the medium. Sonic flow, there is a restriction that under certain locations or some locations the informations are shared, other locations information are not shared. And in a supersonic flow, they also similar thing we have, and here the geometry in a subsonic flow, it is geometric plane is just a line or plane which is passing through this point B. Now, this plane, this line or plane becomes a Mach cone in a 3-dimensional flow field. So, when a body moves at a supersonic speed, all the information related to flow properties are limited within the Mach cone, that is called as zone action, and these informations cannot these informations cannot propagate upstream. So, on the other hand, when you moves subsonic fluid, the flow property informations propagate everywhere in the flow field, and in the intermediate point we have a sonic circle that separates the zone of silence and zone of action by a section or plane XX. Then we will try to see, then we will try to correlate. We talked about Mach wave. Then what is the oblique shock? So, if you recall our analysis of the definition of Mach number, which is a measure of the kinetic energy to internal energy or directed motion of gas as compared to random motion of thermal molecules, that is indicated by a parameter which is Mach number. The speed of the body just above this, when the speed of the body is above the speed of sound, the medium experiences compressions through the formation of Mach waves. So, Mach wave is the initiation of compression, and the dominance of pressure waves progressively increases than that of sound waves. So, first when the disturbance is very small, infinitesimally small, then we call as sound waves. After the strength of the disturbance increases, the effect of compressibility increases, which means medium is compressed, and to what point, when when you reach a supersonic Mach number, that means when we reach a velocity of the object with velocity of sound when they are equal. So, it is the situation for the formation of Mach wave, and subsequently when the Mach wave becomes stronger and stronger, so the dominance of pressure wave becomes more and more. So, which means dominance of pressure wave increases than that of a sound waves at higher supersonic speeds. That means when Mach number increases more than, that means B is your greater than A. Now, if you try to recall this or recall the shape of oblique shocks, it is essentially said in a two-dimensional phenomena. And when these two-dimensional waves extended in the third dimension, we call this as a Mach cone. So, treatment of oblique shock starts with a two-dimensional phenomena due to additional geometrical parameter. Now, other important point is that if you try to have here drawn two particular pictures or schematics of two pictures, one is the case of normal shock, other is the case of oblique shocks. So, in a normal shock, the streamlines in both sides of the shock waves, they are perpendicular to this shock wave and they moves in the same along the same line. But when the shock wave when the streamline passes through an oblique shocks, it tries to deflect along this surface. So, what happens at one particular instance, when the flow is supersonic in the upstream, at one particular instant a Mach wave is formed. Now, when the strength of the Mach wave when this Mach wave is formed, it forms an angle with a angle mu m, which is the Mach angle, and this Mach angle can be calculated as mu m is equal to sin inverse 1 by m. So, this can be calculated from this sonic circle diagram. And when the strength of Mach wave becomes higher and higher, we treat them as a oblique shocks. And when this when the strength of the oblique shock increases, so it forms a normal shocks, which means essentially in a supersonic flow field, when V is equal to A, that is the initiation of Mach wave. Now, when you progressively increase V higher and higher as compared to speed of sound, oblique shock wave starts forming, and one particular when the shock strength, and this shock strength keeps on increasing when you increase the upstream Mach number, and at one particular situation this particular oblique shock becomes a normal shock. So, this is the case what we can say in a for an oblique shock situation, the oblique shock wave angle is higher than the Mach angle, and Mach angle is defined by this, and for oblique shock to become a normal shock, the shock wave angles beta becomes pi by 2 or 90 degree. All other treatments across the oblique shocks is almost similar to that of normal shock. We will try to do those analysis. So, across an oblique shock, the shock Mach number decreases. So, in a normal shock situation, we say Mach number after the shock is subsonic. Now, here the shock Mach number decreases, while the flow is always supersonic subsonic across a normal shock. Other parameters like pressure, temperature, density always increase across an oblique shock. Stagnation temperature do not change, stagnation pressure drops because there is an increase in the entropy. Now, if you give more physical insight in a flow field, I can draw these things as a oblique shock, how oblique shock is formed in a physical situations. So, here I have drawn a surface which is essentially called as compression corner, which means in this complex it consists of two surface, one is horizontal, other is inclined to an angle, and this angle is called theta. So, and across this compression corner a supersonic flow is allowed to pass. So, when it is allowed to pass, a oblique shock wave is formed, which is shown here. Why it is formed? Because the flow tries to compress itself. Why? What is the physical concept behind it? That the streamline, when it passes through this oblique shock, it becomes parallel to this second corner or second line, which means streamline after the oblique shock gets deflected by an angle theta, which is nothing but the angle for this compression kernel. That means, this line and this compression kernel line, streamline and this compressor kernel line, they are parallel to each other. So, if you view this particular event physically, it means that flow bends, that means streamlines bends towards itself. So, it looks like as if the streamlines bends towards itself. So, as if the main streamline feels the compression effect from the streamline which crosses this oblique shock. In other words, it sees that entire flow field simulation feels or flow field feels as if the entire flow gets compressed while passing through this oblique shocks. So, here what I have mentioned here, all streamlines experience same deflection angle across this oblique shock. This is a naturally occurring phenomena in a supersonic flow when the flow has to turn towards the main block of flow through certain flow deflection angle. So, this is what you see the effect of an oblique shock. And what is the difference between a normal shock and oblique shocks? Here we can find out that Mach number is not exactly subsonic, rather Mach number decreases. Other parameters like static pressure, static temperature, all those things increases. So, this is the characteristics for an oblique shock and this is the characteristics for a normal shock. Another important observation we can see here that when you treat this normal shock, it is a one dimensional phenomena because the streamlines do not deflect after passing the normal shock, whereas oblique shock is a two dimensional effect because the flow streamline gets deflected. We need another parameter angle, that is theta or geometric parameter angle theta, to do the analysis. So, it is a two dimensional effect. And entire summary that I can make out here, whatever I have talked so far, we have three angles. One is Mach angle, which is the initiation of oblique shock or at the formation of Mach wave, that is Mach angle mu m, that is defined as sin inverse 1 by m1. m1 stands as the upstream flow Mach number. Then we have oblique shock wave angle beta, and this beta is always greater than mu m, that is quite obvious. Then only the flow becomes the flow Mach number is again supersonic, but it is less than the inflow Mach number, that is m2 is less than m1. Now, when we have a normal shock event, the beta becomes pi by 2. So, this is a normal shock situation. So, this particular picture gives the complete picture about the flow field which involving Mach wave, oblique shock and normal shock. Now, we will move on to second part of this lecture, that is oblique shock wave, that is where we will try to find out the governing equations for the oblique shock and oblique shock relations. So, to explore the governing equation of oblique shock, let us think about an oblique shock as shown in this figure. So, three fundamental equations are of importance. One is continuity equation, second is momentum equation, third is energy equations. To analyze this oblique shock phenomena, we will now see that a streamline which is moving at a velocity v1 is about to cross this oblique shock. So, what we can say is that we can have a phase A and D, and that means the streamline passes through this oblique shock through a phase A and it leaves the oblique shock through phase D. So, A, B, C, D, E, F are we can consider as the area in which the slug of flow that enters and leaves. So, if you look at this particular figure, the direction of streamline and the phase B and F, which is upstream side of the flow, they are parallel. So, B face B and face A, F is parallel to the streamline in the upstream of the flow, and the streamline enters through this face A. Now, when it crosses this oblique shock, the streamline leaves through faces D, and the face C and E, they are also parallel to this streamline when it crosses this oblique shock. So, which means one can say that the face of control volume, that means entire volume, when you this particular face area, when you extend it to volume, the faces of control volume A and D that are perpendicular to the velocity are of importance. Continuity equation is applied as that of normal shock. The faces of control volume B, C, E, F are parallel to the velocity, and then that do not contribute to the surface integral, which is C in this momentum equations. And in this momentum equation, there are two components. One component is tangential, which is parallel to the shock wave, other is the normal component, which is perpendicular to the shock wave. So, what we see here, that same oblique shock, if you try to draw the velocity diagrams. So, this is m1 and v1 is the upstream velocity and Mach number, and we can draw or resolve its velocity component in two directions. One is perpendicular to this oblique shock, other is parallel to this oblique shocks. So, this can be drawn in this manner. So, small v 1 and m t 1, they are tangential component, d 1 and m n 1, they are perpendicular component. Similarly, this is what you say upstream, and in the downstream, similarly we can have the information about m 2 and v 2, they can be resolved, which is in the direction of the oblique shock and perpendicular to this oblique shock. Okay. So, through this, when passing through this oblique shock, the streamlines gets deflected by an angle theta, and oblique shock is sitting at an angle beta. So, with this information, now we will proceed to our equations. So, with basic information that we can get from this is, let us first revisit the momentum equation tangential component, and this gives that v 1 is equal to v 2. Momentum equation normal component gives p 1 plus rho 1 e 1 square is equal to p 2 plus rho 2 u 2 square. So, this equation is almost is the same as that of normal shock. That means, the normal shock component across an oblique shock has same equations as that of normal shock equation. Since v 1 is equal to v 2, the continuity equations can be rewritten as rho 1 u 1 is equal to rho 2 u 2, and energy equation also starts with capital V 1, but ultimately energy equation is represented in terms of enthalpy change, which is expressed in terms of u 2 and u 1. U 2 and u 1 are nothing but the horizontal component of the velocity. So, what we see here is that energy equation and momentum equations across this for the which resembles to equations of that of normal shock. Now, another important information that we get from this geometric analysis, that is in terms of theta and beta. So, and what we can say here, when you look at this geometry of this diagram, I have already mentioned normal component, tangential component of upstream flow, normal component and tangential component downstream flow, that is region 1 and 2. So, we have also talked about the streamline deflection angle theta and shock wave angle, that is beta. Now, looking at the geometry of the figure, we can say if this angle is beta, then we can find out this will be also beta, and this angle will be 90 minus beta. Then we can define a parameter normal component of upstream Mach number m1 is equal to m n1 by sin beta. This from this right angle triangle we can find out. Then normal component, similarly if you look at downstream angle, so this angle is beta, this is theta, and so obviously looking at this figure, this particular angle will be beta minus theta, and this is your m n2 and this is your m2. We can find a relations, that is sin beta minus theta into m2 will be m n2. So, ultimately a oblique shock problems can be tackled once we know tackled as a normal shock problem once we know the normal component of Mach numbers in the upstream and downstream side. That is the catch here. That means, you for a oblique shock situation, you frame a normal shock environment and try to take the advantage of normal shock equations to calculate the flow parameter. So, likewise instead of m1 and m2, we can correlate further, that is m2 with respect to mn2, mn1 with respect to m1. Now, all this static parameter ratio will be now function of mn1, not m1, that is static density ratio, static pressure ratio and static temperature ratio. Then once we know these ratios, then we can also find out entropy change across an oblique shock. Then we have another important equations for an oblique shock analysis, because additionally we need the information to solve a oblique shock information. We require the values of beta and theta. One parameter is additionally required. So, for that we have to we can form a relations what is called as theta beta m relations. The changes across an oblique shock depends on the parameter, on the two parameter, one is upstream Mach number and flow deflection angle, which is given by these two mn1 and mn2. Then now from this geometry of the figure, one can find out that tan beta is u1 by v1. So, this is beta, this is also beta, and this is 90 minus beta, and this will be beta. So, tan beta is u1 by v1. Again, if in the downstream side we have flow deflection angle theta, we have shock wave angle beta. So, this angle will be beta minus theta. So, from this right angle triangle we can say that tan beta minus theta will be u2 by v2. So, thereby we can correlate beta and theta through this relation, tan beta minus theta by tan beta is equal to u2 by u1. Now, you recall these continuity equations, where you can find out u2 by u1 as rho 1 by rho 2, and it is a function of mn1. And here and from this normal shock we can have this information. So, we have relations between m1 and m1 and mn1. So, mn1 information can be put in this density ratio, and mn1 here and mn2 relations we can find out. So, ultimately when all these things is put in this equation, that is tan beta minus theta by tan beta, basically we are putting u2 by u1 ratio in these expressions, and this becomes a trigonometric equations, that is what we call as theta beta m relations. And once we simplify that equation, we say tan theta is equal to twice cot beta whole bracket m1 square sin square beta minus 1 divided by m1 square into gamma plus cos 2 beta plus 2. So, this is the fundamental relations that correlates the shock wave angle beta and flow deflection angle theta. So, this is a very important equations that correlates the angle theta and beta, and which is a function of m1. So, if you know m1 and if you know one flow deflection angle, we can calculate beta. So, this is the catch here and what we call as theta beta m relations. So, this is all about the oblique shock relations, and with this oblique shock relations we will try to catch up on a problem which is how to evaluate oblique shock flow parameters for a given practical situations. So, what is shown here is that a uniform supersonic stream, which is stream at Mach number 3 and pressure 85 kilopascal and 200 Kelvin, that is upstream condition, encounters a compression corner in which the flow deflects by an angle 20 degree. So, essentially if you look at this particular figure, we can say that as if there is a compression corner sitting here, and this compression corner deflects the flow by an angle theta. So, eventually the compression corner angle and flow deflection angle same. So, in the initial conditions you have m1 which is 3 here given, and initial condition it is given P1 as 85 kilopascal and T1 is equal to 280 Kelvin, and downstream side what other angle is given, that theta is equal to 20 degree. So, what is not known for here, that we need to find out all properties, and we need to find out Mach number, static and stagnation properties after the flow deflections. So, entire when the flow crosses, when flow deflects, entire parameter is now governed by this angle theta, and it is mainly governed by the oblique through this oblique shock relations. So, let us try to evaluate this particular problems. So, let us start with upstream case. We have P1 85 kilopascal, T1 is equal to 280 Kelvin. Now, initially we have M1 3. So, we can have the stagnation values of pressure P1 by P naught 1 is a function of Mach number 1 plus gamma minus 1 by 2 m1 square to the power gamma by gamma minus 1. So, your gamma is equal to 1.4 and m1 is 3. So, by inserting this value, we say P naught by P1 is equal to 36.73. So, once you know this P1, we can say P naught 1 is equal to 3122 kilopascal. Now, once you know this, similarly T naught 1 by T1 is equal to 1 plus gamma minus 1 by 2 m1 square. So, this relation gives stagnation temperature ratio that is at 2.8. So, from these informations we can find out rho 1 is equal to P 1 by R T 1, R is 287 joule per kg Kelvin, and this will give rho 1 as 1.05 kg per meter cube, and rho naught 1 is equal to P naught 1 by R T naught 1, and this value will be 13.875 kg per meter cube. So, what we know is for upstream condition of M1 is equal to 3, all flow parameter are known, P1, T1, rho 1, P naught 1, T naught 1 and rho 2. So, this is region 1. Now, for region 2, the streamline crosses the oblique shock. Now, when it crosses the oblique shock, then what information you require first? We require the information about Mn1, and recall that it is M1 sin beta, and this theta beta m relation, and before that we can start the we require the angle shock wave. For this calculation we require shock wave angle beta. So, for to calculate this angle beta, we have to recall this theta beta m relations. So, in these relations what we can do is we have M1 is equal to 3, theta is equal to 20 degree, and when you put this equation turns out to be tan 20 degree is equal to twice cot beta. M1 is 3, that is 9 sin square beta minus 1 divided by 9 gamma 1.4 plus cos 2 beta plus 2. So, this is a equation in which beta is unknown. So, it is very difficult to solve these equations as a function of purely beta value. So, it has to be solved through trial and error. For using this trial and error, how do you approach? So, we have to take an initial guess. So, to have an initial guess, let us start thinking that what should be our initial guess. So, the catch here is that to have a good initial guess, you have to see that oblique shock formation starts with Mach angle. So, let us calculate Mach angle mu m, which is sin inverse 1 by M1. So, M1 is 3. So, this Mach angle can be calculated as 19.5 degree. That means, and we also said that beta is more than mu m. So, from this 19.5 degree you keep increasing, try to solve left hand side of the equation and right hand side of the equation. So, if you match this value, keep matching, then one point of time we can find out this beta value as 37.5. at which LHS equal to RHS. So, we can now say that beta angle, the shock wave angle beta is 37.5 degree. Now, once we have this 37 shock wave angle, we can calculate Mn1 as M1 sin beta, that is 1.826. Then we have, so now we can again find out Mn2. We can, for this Mn1 we can use normal shock table. So, normal shock table for this Mn1, that is M1 is equal to Mn1 1.826. So, you can refer this particular extract of normal shock. For M1 is equal to 1.826, we have information about P2 by P1, rho 2 by rho 1, T2 by T1. So, this will give you Mn2 as this 0.6121, P2 by P1 3.698, T2 by T1 is equal to 1.547, P naught 2 by P naught 1 is equal to 0.8038, and M 2 is equal to M n 2 divided by sin beta minus theta. So, beta is 37.5 degree, theta is 20 degree. So, this will give you M 2 is equal to 2.04. So, basically M 2 is known as in the downstream Mach number, which is 2.04. Now, with this information, now we can calculate P 2 as, so with this M 2 is equal to 2.04, we can say P 2 is equal to 314.3 kPa, because we know the ratio of P 2 by P 1. Then we have T 2 is equal to 432.2 Kelvin, and rho 2 would be P 2 by R T 2. So, this value is 2.53 kg per meter cube. So, this can be shown is that rho 2 is equal to rho 1, and also density, static density is higher. Then once we know this Mach number, we can use this isentropic relation of P naught 1, P naught 2 by P 2, which is for M 2 is equal to 2.04, which will imply P naught 2 by P 2 as 8.32, T naught 2 by T 2 is equal to here static temperature do not change. So, we say T naught 2 is equal to T naught 1 784 Kelvin, and rho naught 2 is equal to P naught 2 by R T naught 2. So, this is 11.6 kg per meter cube. So, likewise, we have M 2 M 2 2.04, P 2 T 2 rho 2, that is static value, and P 2 since P 2 is equal to 314.3. So, this will imply P naught 2 would be 2615 kPa. So, we have these values, we have stagnation value. So, what this problem gives an indication that across an oblique shaft for a given Mach number and given Mach number and flow deflection angle, the both upstream and downstream parameter can be calculated. So, with this I stop. Thank you for your attention.